Okay. So, like I said, I've got about 9 questions for this review. It's not all encompassing, as I mentioned, but it should be a pretty good start for your review. So, again, just for the sake of the recording, I'm going to restate that I will be posting the solutions to the free response questions from the review to Classroom at some point during the day. And what else was I going to say? Oh, yeah. Make sure you study the review guide that you were given at the beginning of the chapter, because that is built off of the test itself. All right. So I'm going to close the door. We are going to begin. All right. So again, just kind of watch as we go through here. So this question, objects can possess energy as what types of energy? Now this is going all the way back to the very beginning of the chapter, okay? So objects can possess energy as what types? Now this type of question is going to be a multiple choice question, okay? So you don't have those choices here, but just to get your thought going here, they can possess potential and kinetic energy. Okay, what is kinetic energy? It's the energy of motion, movement. Potential is the quote-unquote potential energy that an object possesses in accordance with their position, their charge. Okay, so depending on where they're located. Oh, also their shape. So know those 2 different types of energy that we discussed way back in the beginning of chapter 5. Question 2, excuse me. Under what conditions would always result in an increase in the internal energy of a system? So here we are talking about internal energy. We talked about 2 major aspects that are used to determine the internal energy. Okay, that is heat and work. So what must happen to the system in order for it to always have an increase in internal energy? Okay, because there's a really simple math calculation that we can use. In order to always, and the key word is always, okay? The key word is always. The system must gain heat and the surroundings must do work on the system. Whenever the system gains heat and work is done on the system, you will always have an increase in internal energy. Now, if the system gains heat, but the system itself does work to the surroundings, you're not always guaranteed to have an increase in internal energy. So these are the parameters that would guarantee you an increase in internal energy. Which of the following is a state function? Work, heat, enthalpy, or Q? Well, first off, Q and heat are really the same thing, right? And so work is part of that calculation of internal energy, okay? And we talked about state functions and all that stuff about midway through the chapter. And it said that work and heat, therefore this, and this, are not considered to be state functions because they're kind of the middle portion. And we don't really care about the middle portion. All we care about is how the system started and how the system ended. And all that leads up to enthalpy. So enthalpy is a state function. Question 4 asks you, what are the units of specific heat? Now, again, we talked about specific heat and how it's a measure of how much energy is going to be required to raise a gram of substance 1 degree Celsius or 1 Kelvin. So when you think about that, and you think about the formula that is used to calculate specific heat, which, again, you'll need to know, but again, it's open notes, basically, open material, with the exception of a book, for your test. This is what you would have for your units. Again, this is not a minus sign. This is simply like joules per gram times gram Kelvin or joules per gram degrees Celsius. That is not a minus sign. Okay? Not a minus sign. There we go. Made it really clear in the video. All right, question 5. We're trucking right along here. What does standard conditions mean? This came from a slide that had like 6 asterisks after it. So I said, you need to know, what does it mean to have standard conditions? Okay. That means you have 1 atmosphere of pressure and a temperature of 298 Kelvin, or you could even say 25 degrees Celsius. But, you know, if we're sticking with the authentic measures, it'd be 1 atmosphere and 298 Kelvin. Okay, now we're going to get into the math and part for the last 4 questions or so. Again, if you want to try and solve this, you can. Otherwise, I'm just going to talk you through it and show you the setup and everything like that. So question 6 asks for, at what velocity in terms of meters per second must a 720 gram object be moving in order to possess a kinetic energy of 1.25 joules? So, again, we've got a 720 gram object. What velocity must it have in order to obtain a 1.25 joule kinetic energy? So, here is the first general equation, okay, where you have kinetic energy, as your book labels it, EK, equals 1/2 mass times the velocity squared. And so we are going to rearrange this equation to solve for velocity squared. Now, what have we said about the mass that needs to be in here when we calculate this? What unit does it actually have to be in? Does that have to be in grams or something different? Kilograms, yes. Make sure your masses are in kilograms. So to convert this, you just divide this number by 1,000, you get 0.72 kilograms. Okay? So when you rearrange it for V, you get V is equal to the square root of 2 times kinetic energy divided by its mass. Don't forget that in the original formula, V is squared. And so we are only solving for V. So when you isolate it and rearrange for V, you have to take the square root of itself and the other side of the equation. And so when you do this, you get 1.86 meters per second. So that object must be going at 1.8 meters per second in order to have this 1.25 joules of kinetic energy. Question 7. A 22.44 gram sample of iron absorbs 180.8 joules of heat, upon which the temperature of the sample increases from 21.1 degrees Celsius to 39.0 degrees Celsius. What is the specific heat of iron? So again, thinking about the formula of specific heat, you have S, which is specific heat, is equal to Q, which is the heat transferred, divided by the product of mass times the change in temperature. Now, in this case, for the case of specific heat, you must make sure that your mass is in grams this time. You see it in the unit itself, okay? It's right here. So, you have the heat transferred is the 180.8 joules of heat. That's your Q. You have your mass, 22.44 grams. Don't have to make any changes to that. And multiply the mass times the change in temperature. You take your final minus your initial, so 39 minus 21.1. Put that together, you get 4.5 times 10 to the negative first. You don't have to put it into scientific notation. It's just good practice. joules per gram degrees Celsius. So again, review the sample problems. Review the sample problems that we did in class when discussing specific heat. That's why we do them, so you can go back over them, and I hope you write them down as we go over them as well. Okay, this next question is talking about Hess's law. Again, let's just talk about how we solve this. This particular question is one we've already done. So I'm going to check it in on you to see how you'd go about solving this. So we have we're to calculate delta H for the following reaction where we have NO gas plus O gas yields NO2 gas. And so we have these three equations that we need to manipulate. So let's start looking at the three equations. First one has NO gas on the correct side of the yield sign for our target equation and the same quantity, so the same number of coefficient as our target equation. So I'm going to actually just leave that there. But another good thing is we also have the NO2 gas in this one that is on the correct side. So this first equation I'm not even going to bother with. Okay? Not even going to bother with this one. So really all that we need to start focusing on is the oxygen, but we still have two that remain here. So in our second equation, we see that we have O3 on the left side here. But in our first equation, we also have it on the left side here. We need to eliminate that. And the only way we need to eliminate, or we can eliminate this, is make sure they are on opposite sides of the arrow in our final kind of net equation. So what I'm going to do is, for the second one, I am going to flip the equation. Okay? And when we flip the equation, what happens to the sign? It changes. So this will now be a positive 142.3. So to recap, first equation, don't do anything. Second equation, flip it. When you flip it, you're going to change that sign. Third equation. So now, in my third and final equation, I see that the product side of the third equation has my single oxygen here. But in the target equation, it's on the left-hand side. So I'm going to need to flip this third equation. But before I do anything crazy, I also notice that after I flip it, that the coefficients aren't going to match up. So for this third equation, I'm going to flip it and divide everything by 2. If you're the individual who likes to say, I'm going to multiply by 1/2, so be it. Same thing. So third, flip and divide by 2. And don't forget what you do to the equation, you must do to the enthalpy value because it is an extensive property. So when you start messing around with the quantity present, you're going to be changing the amount of energy change. Okay? So first one, no change. Second one, flip. Change the sign on delta H. Third one, flip and divide everything by 2. Change the sign and divide delta H by 2. Once you've got all that done, you're going to add up all of the reactants on the same left side. You're going to add up all the products put on the right side of the arrow, and then you begin crossing off what is on the same on both sides of the arrow. And so when you do that, you find out that your equation matches, and you will find, then once you determine that, you then sum up all of the enthalpy values, and you get an answer of negative 304.1 kilojoules. And as I just mentioned, this was example 5.9 in practice. We did this in class. So if you kind of got stuck while I was walking through it, then go back to your notes. I hope you follow along with it when we're doing it, and take a look at that. Again, it's just Hess's law. And lastly is when I'm going to want you to have your appendix C out. Okay. So we have ethanol combusting with oxygen to form CO2 and H2O. Again, with these questions, it is extremely important for you to pay attention to the states of matter. So ethanol, C2H5OH. We'll see here in your appendix C, I want you to try to find it, but in here, ethanol is going to have a value of negative 277.7. I want you to locate it in appendix C. You find it? Excellent. You find it, Colton? Excellent. Okay. What about oxygen? What's oxygen's value going to be? 0. And I'm just going through the line here and just picking out having you find the values. Okay, we're going to remind you how you set this up. Okay, so yes, oxygen is going to be 0 because it's in its elemental state, elemental form. Okay, what about CO2? Gas. Negative 3. There you go. Negative 393.5. Perfect. And lastly, H2O as a liquid. H2O as a liquid. Negative 285.8. Very good. Now you got to be really careful because even as you see here on 5.3, you've got water, two versions of water right next to each other. And there is a pretty significant difference between their enthalpy values. So, again, can't reiterate enough. Make sure you know the states of matter. So, how do we calculate this? Well, you take the enthalpy values of the products multiplied by their coefficients. So, when you set this up, you'd have 2 times negative 393.5 plus 3 times negative 285.8. Okay, so it's the sum. I forgot to put the sum symbol here. It's the sum of the enthalpy of the products minus the sum of the enthalpy values of the reactants, again, multiplied by their coefficients. I'll say a better version is found in your notes. I actually decided to add this at about 8:03 this morning. And as you see here, I'm used to saying it, but I forgot to include the special symbol. So yeah, go over your notes in conjunction with your review guide. You will be just fine, okay? When you take this, if you're taking it in class tomorrow, make sure you have your calculator. Make sure you have your notes. Make sure you have your appendix C, okay? Anything you might need within reason, okay? If you have a question on whether or not you can use it, ask me, okay? But we'll cross that bridge when we come to it. But yeah, again, this review's a little different because I just wanted to walk you through some of these questions because some of the questions were more specific. That will be more of a multiple choice question. So I just want to kind of get those out there. And these math questions, we've seen examples time and time again. I just wanted to make sure that we walked through and just kind of revisited some of that. So questions on the review. Again, go over your review guide. Go over your review guide. Here in just a few minutes, I'm going to post the solutions to the free response on the review guide. Look over those. Trying to give you all the legs up, I guess is the saying, that you could possibly need for this test. Okay? So, if there are no questions at home, I'm going to stop recording.